everyone. Um, Today we'll be going into something really interesting. It's more so, again, mathematical, and gives some very novel insights about the physics that you do, that you may not have seen if you did only physics. So there are some analogies between different theories that you can see when you start working with this. So we'll go into manifolds and bundles and things like this, but we'll construct it in a very pedestrian way. And so I'll start with this simple question, I guess. Let's say you have a set of points, all right? Some points, you can even have things like just the set of 1, 2, 3, so on, whatever, or a set like this. Now, I want to make this a space. How would I do this? So I have an intuition of what space should be from my physical experience. But at this point, we're making the transition into the Platonic ideal space, where I want a space there. So yeah, what does space mean to you guys in this sense?
Where you can take some part of the space and another part of the space and maybe do something with it.
Okay, so you want to, I'll call it relate two parts of a space, yeah? Of space. We still don't know what space is, so we're defining it through its qualities. Yeah, so do you guys have any other ideas about what space should be? This is a very good start.
Okay, well, before I say the two things in the space, let me just say there must be something in the space.
Something in the space, I see. Okay.
Yeah, or else the space would be empty. And okay, oh yeah, that's true. Empty
yeah,
also.
okay. Thing contained in space, okay. But
or
or
like the space itself, because you can have an empty space also, but the space itself exists.
Okay, so or rather existence of space, rather existence of some kind. Okay.
Yeah. So I was saying that space can be thought of as a certain arrangement of points.
This is very nice. So you have arrangement of points. Okay. Okay. These are all wonderful answers, and this is what we'll focus on. So in order to bring it into existence.
So just a clarification. When you said two parts of space, are we talking about just space, or are we trying to relate two objects in space?
Abhiram, you want to answer that?
Yeah, I wanted to say the second point first, that we must define some sort of existence, and then I can say the two objects of the space.
Right. Yeah, because it's like a way to define two objects relative to one another.
The second point should have come first.
Right. No. That's what struck to my head when you said that.
Yeah. Okay, perfect. Yeah, so these are all very good answers, and we'll build up on this. So, yeah, you did mention objects in space or things like that, but you also mentioned space itself. So we want to find relations between two regions of space. And Muskan also mentioned this arrangement of points in space. Now you have the concept of arrangement and relation and coming in. So we start thinking about the lines along which we find relations between points such that it gets into an arrangement, right? Now, what are the relations that you can think of between these points? What is the simplest relation that you can think of, let's say?
Equivalence.
Yes, okay. So if they're equal, equivalence, okay. What else? You can, yeah, like what are different relations that you can build, like intuition wise? Like, I'm not asking for any mathematical definition. If I have to relate this part to that part, this set of points to that set of points, how can I relate it?
Like you can just translate, adding some constant value.
Okay, yeah, you can translate, but I should tell you, all we have is a set. We don't have any other structure, but yes, okay, translate. That is good. Translate to there, wherever there is. Now, yeah, go Muskan, yeah.
So with translate to there, we can think of where those points are. So if some points are here and there, so
yes,
their position, how close they are, how distinct they are.
Correct. So we are getting close to this concept of near and far.
Yeah.
So this is the most simplest relation that you can come up with between points, whether they are near and far. Now, let's see if we can build a mathematical structure that will tell us if it's near or far. And we want the simplest structure that we can build. Now, the word translate also encapsulate this in some way. But when you said translate, add something, you have to introduce the structure of addition. What constants are, all of this. Can we do it without anything, like bare bones? And yeah, you can start doing this by introducing groupings of points, right? So let's actually say that I have some points like this, okay? First, I have a group which includes everything. And let's say I have a group which includes, or rather a set of points that groups it like this. And let's say I have a set of points in this way, and so on. Although I'm drawing it very visually here, do note that there is no notion of distance. Okay? So yeah, I know it can be a little bit difficult because we tend to think of distance already, but there is no distances or anything here. It's just I'm forming sets, that's it, of points. Yeah, but this is not very helpful to write, so that's why I drew it. That's it.
So it's similar to saying equivalence, right? What Abhiram told.
Exactly. Yeah. So it connects back to equivalence as well, and we'll see how. So now I'll take this point A, and this to be point B, and this to be point C. I want to see which point is nearer and which point is farther. And to do this, I employ a very simple rule. What could that rule be?
If they lie within the group.
Within the same set, right?
Set.
So first, let's say you have this set. At this level, they still lie. These 2 points still lie in the same set, right? Okay. Next, I've drawn it very confusingly for myself, but okay, this set. Okay. They still lie. Okay. Up to 2 levels. They're still there.
Right.
Next, I'll take this set. Now we found a set that contains the blue point, but does not contain the just a second, sorry. Yeah, it contains a blue point, but does not contain the green point. Now, I take another set, which is a subset of all the original set, which is this. All right. Now, in all these sets, we still see that the orange point is still there. So the orange point is still within the same set as the blue point, but the green is already gone. So in some way, the orange point can be said to be closer to the blue point than the green point. And this is the idea of neighborhood. All right. So we've somehow invented the notion of closeness using just sets, nothing else. And now what we do is we actually construct the set of sets. All right. So we need different kinds of sets. So I'll call this set sigma. Okay. The set of points is sigma. So I'll construct something called sigma and the topology. Now, what is this? Right? It's a fancy name. It is just, it's nothing but the set of certain sets of these points. And it has certain rules. The topology includes the entire set and the null set. The set containing those sets belongs to the topology. It has certain subsets, right? That is what we did. But now we wanted to see how different subsets relate to each other to define closeness and farness. So for this, what we do is we take unions of all the subsets. So instead of saying unions, I'll just write this. And subsets. Okay.
So in the topology, we have all the subsets possible or only certain subsets?
That is for you to decide. So that is more freedom. So it is up to you if you want to make some points nearer to others. Right? So that's why I said there is no distance of notion yet. You are introducing it. So it's up to you totally to make some points closer than others. And this is how you have some freedom. So you can take the set of all subsets as well. Or you can even get rid of all this and just take these two. These two are still subsets, right? And this is called a trivial topology. But this is a must, though. You need to have all the unions of the subsets you've chosen and finite intersections. We don't need to really worry about why it's finite intersection right now, since this is more of an intuitional introduction. And this is a topology. So you've made something a space.
Right. So when we have only the sigma and null set, that means all the points are close to each other in the space.
Yes, all the points are equally close to all the other points.
Okay.
Yeah, correct. And now, and these subsets that I said are called neighborhoods, or they are also called open sets. Why do I call them open sets? Because it's just convention, I guess, that they belong to the topology. And there is some relation to the complement of it being closed and clopen sets, sets which are both closed and open, which are both the null set and the entire space, but we don't need to worry about that right now. We call them open sets. Okay. So you've constructed a space. Okay, nice. You have some notion of near and far.
So what would open really mean in terms of nearness and farness? Does it have any significance?
It does. When you're considering, let's say, a point on the boundary. Let me use a different color for this. Yeah. Let's say there's some point on the boundary. Now, since these sets are actually open in the mathematical sense as well, that when I consider this set that belongs to the topology, since it is open, this point does not belong to this set. So it in this neighborhood of that, the blue point, whatever. So you've already, found some boundary to where the closeness stops or the closeness starts. Yeah.
Okay.
Okay, perfect. So you have a topology now. Fine. But now for physics, how is this useful? Fine, you have a space, but what additional structures would you need if you want to solve physical problems here? Can you think about things? Which is like the absolutely most important structure that you can construct on the space.
Distance?
Correct. Distance is something that's really useful. So let me make a note of that. Yeah, I think I'll just keep it like this so that you can see the previous things as well.
Yeah.
You need distance, yes. Is there anything else? What is the nature of the problems that we solve in physics? Yeah.
No, I mean, I feel like when you especially emphasize on the open sets, as you explained itself, like, so the boundary must also be a important factor. Like just
fair
like
enough.
distance.
Yes.
So like
boundaries. Good. What else?
Origin.
Okay. We'll come back to this because this set of episodes will culminate into the choice of origin in a certain sense. Uniqueness, okay. Well, yeah, I'll add it to the same point, uniqueness, because even that will probably connect back. But I feel like so what does physics study? If everything is just as it is, there wouldn't be much study. It would be just a fact. How do we study physics? We study
some kind of relation between these subsets.
Okay. Relation between subsets. Okay. Other relations.
Something like if you translate if you translate to different sets, something remains invariant.
Okay. Yeah. Okay. But we'll actually look back at translates again. So what does this actually mean? That there is something changing.
Yeah.
So what you actually study is change in relation to all these points that you have. So if you have to study changes, we know from basic calculus that there must be a differentiable structure on it. That is, you need to have derivatives, slopes. Derivatives are just glorified slopes between two variables or whatever. So you need differentiable structures. So we'll see how these things as well come into play as soon as we add the differentiable structure. So we will see that the differentiable structure is more fundamental than all these other structures that you just mentioned. Another thing, go on.
So when we say a differentiable structure using only what we have discussed till now, does that what would that mean really? That how points in a given set are changing with respect to the points in the other subset?
Correct.
Something like
Correct. Yeah. So we need a way to compare subsets.
Okay.
Okay. So we will cheat a little bit here, but we'll get to the cheating part. But coming back to topology, so now with just this structure, right? What are the things that you can do? So all you have to do is maintain this structure of sets intact. You can do anything else with it. So you can stretch the space. You can twist the space, but you can't tear it because you'll be tearing the subsets, which you should not be doing. And you shouldn't be gluing. So when you glue, what happens? You're actually changing the subsets again. So that is how the notion of or topologically invariant things come from. That's the famous or the donut is the same as a coffee mug, and all these things come up that people may have heard. It's because you're not changing the subset structure. All right.
So if we are defining a space using these subsets, what do we mean by stretching the space?
It doesn't mean anything. So that is why we can do it.
Okay, it's invariant. The space remains.
Yeah. Like mathematically, you're actually not doing anything, even though physically you're like, oh, I'm stretching it, but it's not changing anything with respect to the shape. So stretching and everything is an intuition that we have. Math doesn't see it yet. Once we define distances, we'll be able to see it.
Okay.
Right? Okay. So now we'll come back to the cheating part. So now I'll draw some space like this, and I'll assume that it already has some topology. We've already constructed it. And now what I want to do is how do I add structures that sound like derivatives to it? I need a notion of a tangent space or something, and these sort of things. But in order to do that, I need more structure in the space in terms of distances and so on.
Like continuity.
Yes, continuity, exactly. I need something that's continuous and so on. So what I'll do is, go on.
What is the intuition behind thinking it should be continuous?
So if it's not continuous, if there are skips in the way it changes, you can do physics still like that. But most of the phenomena that we deal with, approximately at least, appear to be smooth. And the theories that we construct is that they're smoothly changing, unless you get into some theories where there is inherent discreteness, for which this language doesn't work exactly. You'll have to modify it a little bit. But this is while considering things that are changing smoothly. So you need continuity and things like this.
Changing smoothly in space.
In space.
So for quantum mechanics, it won't work.
It will, provided we are not working with these tools in a real space. We are working in another space from which we can derive information. Yeah, but we'll get to that soon enough. So what I want is, so I want some notion of flatness to actually try to map out things even globally. So if it's locally some sort of, if I can have a coordinate system there or something of that sort, I can try to measure things now on that space. And that is what we'll try to do now. So I'll zoom in a lot, okay? And I'll zoom in further here, where this one point looks like this, right? So what I'll do is I'll map this, okay? mapping is just assigning to each point another point somewhere else. I'll map this to the real line. And this is the cheating part. Because I've already constructed the real line. I haven't told you how to construct it from a set of points. I don't know. I haven't, yeah, there's a notion of distance already here. I haven't told you how to do that, but we've already done it through other means. Your analysis people have already constructed it and given this tool to you, and you will happily use it. Okay. And now this is how you may have coordinates on your space, and you have distances and all of it. You have a notion of it at least, because this already has a certain metric, that is a distance associated with it. Okay. But now, if you can't do this to all manifolds. I mean, all topological spaces. There is a certain requirement where you will be able to do it. And that requirement is, if you look at something locally, if you zoom in enough, it should look Euclidean. That is, it should look flat, like a flat space. In any dimensions. One dimension will be just the real number line. 2 dimensions will be the plane. 3rd dimension will go like, okay. There we go. 3rd dimension will go like this, and so on, even in higher dimensions. Something that looks locally Euclidean, a space that looks locally Euclidean, is called a manifold. There is another mathematical definition for this, which we won't get into, but for the more inquisitive viewers. Yeah, go on.
I was just thinking, when we say that a manifold is Euclidean, right? That is because you said it is locally Euclidean. But like what I was thinking was, if you have, like, let's say we take like some small like balls or something, the spheres, and we arrange them in a circular order. But then we zoom out and then we see from above, it'll just look like a circle.
Fair enough.
And then as we zoom in, we get to know that these are spheres.
Right.
So in a sense, from that perspective, it is Euclidean. It's just a circle. But then as we zoom in, it is non-Euclidean.
Well, but then, no, the whole point is, if you zoom in, it should look Euclidean. So what you said about us constructing this thing out of spheres or whatever, circles. As you zoom in, you see that it's actually not flat. These things are, there is certain surgery happening and it's actually not flat. So this is not a manifold.
Yes,
but
it's not.
Yeah, that is correct. So this is an example of something that's not a manifold. But if you want to go one step further, and those circles, if you want to zoom into that, and there you see that locally it is flat.
Then those individual components are manifolds. No, what I was trying to say is like, in a sense, if we can somehow define a perspective, then we can say that in this perspective, it's Euclid, because even the circle itself, right? If we zoom out, back, it becomes a point or something like that.
Right.
We zoom back in, it becomes a circle, and then we zoom again, it becomes a real line.
Right. So what you're saying is, under a particular scaling,
yes,
it's a manifold.
Yes.
It is Euclidean and it's a manifold. Yeah, one could consider that. For example, let's say we have a circle like this, and we can just draw a tangent, and we say, oh, because we can draw a tangent to the circle here locally, it should be flat, and so it's a manifold. But let's say if you zoom in, you'll see that it's made of these circles. So you zoom in enough, beyond a certain threshold, it stops being a manifold. That's actually very interesting. I am not sure if like there are scale dependent manifolds, but that is something that we can explore. Probably on the next by the next episode, if we have some insights, we can share. But
go on. I was thinking that this sort of when you look at it like this, then you can open your I mean, at least extend your horizons to the, like, we can say that non-Euclidean, like sort of manifold where you zoom in and it's not real line, but well, that's sort of those sort of structures.
Yeah, and these sort of structures, if they are present, or if we can define it in a mathematically consistent way, even if it's not present, would be extremely useful for quantum mechanics. And more so problems of geometric quantization, in a sense, in a very roundabout way, I guess, where you bridge the gap between the classical and the quantum regimes through some definition like this. That will be a very fascinating thing to look at. Maybe next we'll make a note of it by next time. If we can go into it, it'll be great. Okay, awesome. So do note that the definition I've used is a bit circular. I've said, like you can do the Euclidean mapping if it is flat, but the very fact that it is flat is because you can do a Euclidean mapping. So it's a bit tautological in the way I've explained it, but it is to appeal to your intuition that I explained it in this way. But the definition is that it is possible to have a map to a Euclidean space, then it is a manifold. Yeah. Okay. So you have all this structure. That's great. Now you have manifold. So what I'll do is at every point or locally, I'll map it to a separate Euclidean space, because locally I can map it, even though globally it is jagged and all of that.
So I just had one.
Yes, go for it. Yeah.
So when we say that we're locally mapping it, how do I ask this? Okay, so how do we actually define the neighborhood of one manifold, let's say? Or I'm not sure.
This is a good question.
My question is.
No, this is a good question. You know where the neighborhood structure already comes from, though. The neighborhood structure already comes from the topology. So to each subset in the topology, if you can assign a map like this, that would already define something called a chart.
Okay.
Okay, so you have different charts for each subset. And what is a collection of charts called?
Atlas.
It's an atlas, right? So,
okay.
Yeah, the set of charts is an atlas, and I'll denote it by A. So a manifold is actually a triple, where it has the set, it has the topology, and an atlas. Oh, sorry.
Okay.
And now you have a manifold. So maybe we can stop around here. And one thing that we can maybe look into before the next call is, fine, you have an atlas, a manifold. Now, what are the structures you need to actually define a derivative? Okay, on this very abstract manifold that we have constructed. So I briefly mentioned what is needed in this talk itself, on this episode. I just mentioned that word. But yeah, we can go more into it. And from there, we'll be constructing even more structures on it. And we'll find a way to relate general relativity, okay, and electromagnetism. At least in rather QED, quantum electrodynamics, in a very analogous way. This is not an equivalence principle. This is not a solution to quantum gravity. But we'll see how the same tools are being used in different settings. And also for fields like the electroweak force. And even strong force. So in all these forces, we'll see how similar structures come up. So what we'll actually get at is what it means to be a force in a very geometric way. Yeah, this is a trailer for the coming episode. It may take 1 or 2 more episodes, but let's see how it goes. But I think this is a good place to stop, unless you had any other questions.
I didn't have a question, but I just wanted to see if the way that we initially, right, when we saw that we define different sets and we reduce the sets, and that's how we defined closeness and all those stuff. If there's another way to define it.
Okay.
Instead of taking subsets,
right,
maybe something else, and define this like we need to define something like closeness only, but using another way instead of using maybe subsets.
Yes, there definitely might be other ways. We can actually take a couple of minutes to think about it, if there are any other ways. Let's see.
I guess.
Go on. Yeah.
So the thing I thought was like, I mean, could you go back to the diagram?
Yes.
Yeah. Okay. Yeah. This one's fine. This is it's a sort of like, it's a funny way to think about it, but if you put like a wall here perpendicular to the diagram, and then throw the diagram at the wall. So the blue one will hit first, and then the white point, and then the orange. What is that? Green, I guess.
Right. Yellow and green. Yeah.
Yellow point, and then last the green point. And I mean, in that sense, it's like a map to R, and whichever is closer to the bottom of the thing you have drawn here. Like if we define the start of this rod here, right? Like the bottom of this, and whichever point is, I don't know, in some way, like see, like the point is like the blue one will hit first, and then the white one, and then like in that way, it's close.
But there is a pitfall here.
Yeah, I mean, you can throw it in. If I throw it in another direction, then I'll get another
correct
value.
Correct. But there is a fatal flaw in the way I've drawn it, in that I've assumed orientation and distances while drawing it. What you should actually be thinking about is this. So how do you define a wall when you have, okay, let's say I have 5 points or whatever, how many other points that is, yeah. How do I define a wall here?
Okay, yeah.
So yeah, I apologize for this diagram that we have, but it's a lack of our abstract faculties, rather than the lack of math. So yeah, it is a sort of misnomer.
Can we think of it like projection?
Okay. Yeah.
Like,
So this idea is good and it is projection. What
But
Aviram
we'll
described.
already have to define what an origin is, and wherever we're
Yes.
projecting to, we'll need a metric to decide
Yes.
which.
We need all these additional structures.
So I didn't.
Yeah. But if we can have any other intra-set relation rather than just a subset, that would be a way to go. So if we can define an ordering is still, it is a logical operation. So it is fine. We can define, let's call this A, B, C, D, E, or actually A1, A2, A3, and so on, and AI less than AI plus 1. So now you have some notion of what is far and what is near by going along the chain of things. This is still a very bare bones structure because all we are doing is using, we are using the subset idea in a disguised format, is what I.
But we'll have to still define the ordering.
Yes.
As in like what we are ordering.
Yes.
And in different orders, it might be different.
That is okay. Yeah, that is equivalent to choosing different subsets for neighborhoods. Yeah, that is okay. But in order to define ordering, you're actually evoking set theoretic axioms.
Yeah.
Those set theoretic axioms, specifically the one which you're invoking, is inclusion. Inclusion is the same operation that you're using with subsets as well. So again, even if we go about it in a roundabout manner, we are coming to the subset structure again. So it is all the same if you were to define a topology like this. But still, even if it seems impossible, I want you to think about this. If there is another way, that is the challenge by the next episode. If there is a non-inclusion way of thinking about near and far, you can go ahead with it.
And we're not considering evolution of this system, let's say, over
Not
time.
yet. Yeah, not yet.
Yeah.
So that's another coordinate that will be. Yeah. So yeah, we haven't gotten to coordinate systems yet. Yes, perfect. So yeah, you can think about that and question, and also about what it means to have a derivative in this space. Yeah.
I also have one more question. Why do we choose only the flat space to map everything to the flat space itself? I mean, it sounds very intuitive and we understand flat space, but why first place? Is it because we understand it better, or does it have something to do with the physical systems itself?
Okay, this is slightly leading into the answer for the question, but that is actually a very good question. What we are trying to do essentially is, first of all, find distances, orientation, direction, and all of this for art. But you're right, we could technically map it to some other space, and it would no longer be a manifold, but it would be something else that we can compute. But even like let's say you map, instead of mapping it to flat spaces, I start mapping these things to circles, points on a circle everywhere. Okay, or even a torus. A torus is a donut, so I map it to donuts. So if I were to do this, in order to analyze the space itself, my natural instinct is to linearize it. That is, to zoom in and see patches on this, which are flat. But if I am again not sure about this. We can talk about this on our next call as well. If there is a way to talk about these things without linearizing them, that would, I think, be a valid way to go about physics as well.
I think it's in general, a human mind has this tendency to, simplify everything and then
Right.
try to
And then
understand. I think we try to simplify to the most fundamental, basic,
the
simplest
ideal.
things. And then, yeah.
Yeah.
And
Yeah.
then we build on the complexity and understand the complexity. So I
Right.
think that's the reason
Yeah.
we do this.
Yeah.
Yeah.
But yeah, we can actually, yeah, but that doesn't mean that this should be the only way, just because we try to simplify it. So we can maybe think about if there are
Yeah.
other ways. I wouldn't try to call it a manifold. I'll call it an anyfold. Because yeah, I want you to use anything else. Yeah. Okay. That's how anyons were named. They're particles with not just fermionic statistics or bosonic statistics. They can have any statistics in between, but they're called anyons. They are really important in condensed matter physics, but yeah.
Like during their evolution, they can change from bosonic to fermionic like that?
No. Like you have half spin particle statistics and one spin, right? This can have anything in between 0 and 1.
Oh, okay. 1/3,
Yes,
like that.
yes, all of that. Yeah. Anyway, with all this we learn, we can maybe attack that. It belongs to the field of Chern-Simons theory. Yeah. Okay, awesome. Anyway, I think this is a good place to stop. We have a lot of questions to ponder upon, and we'll meet on our next episode. See you all.